Okay, class. I hope my slides are visible to you and I'm well audible to you. So I welcome you all to today's tutorial, which is the fifth tutorial for the course Symmetry, Stereochemistry and Applications, which is conducted by NPTEL, whose course instructor is Professor Anshuman Roy Chaudhary from Aizer Mohali, and I'm Deepika, your PMRF teaching assistant for this course. I'm doing my PhD in chemistry at IIT Bombay. So till now, we have conducted 4 tutorials for this course, Symmetry, Stereochemistry and Applications. And we have been solving related questions for the same course. And in this week, in the 5th week, the main topic which was covered was topicity in organic molecules. So we are going to solve a few questions today on that topic, and also we will cover a few questions on RS absolute configuration in organic compounds. So let us start from the first question. For each of the following, identify the relationship between the two indicated protons and determine whether they are chemically equivalent. So here in this molecule, this is a tetrahedral molecule given where the bond angles will be almost equal to the ideal tetrahedral angle. And this carbon atom is having 2 fluorine atoms substituents, okay? So it is difluoromethane. And if we look at these 2 fluorine substituents, these two are actually in the same chemical environment. And if we replace any of the fluorine atoms by any other group or substituent, in both the substitution cases, we will get the same molecule back, okay? Like replacement of each of these fluorines with some other group will give us identical molecules. Hence, in such cases, as we know that such protons will be called as homotopic or chemically equivalent. I hope this is clear to you. Let us move to the next molecule where we have to identify the relationship between these two protons. So here, if you look at this molecule, imagine this molecule as having a cyclopropene ring, which will be a planar ring, and above and below we have 2 protons. Okay, Suppose we are naming them as HA and HB. So if we replace HA and HB, we will have to check whether we are going to get the identical molecule or enantiomers or a pair of diastereomers. Suppose we are going to replace this HA by a deuterium atom. In this case, we are going to get an absolute configuration for this particular carbon. Let us assume we get it as R. This is just an assumption. We are not figuring out what the exact absolute configuration is going to be. Okay, we are just assuming that the center is having R configuration. Okay, so next, if we replace HB by a deuterium atom, the absolute configuration will now be reversed. Okay, if it was initially R, this time it is going to be S, because these two are in exactly opposite faces. Hence, we can conclude that replacement of any of these protons are going to give us a pair of enantiomers. Okay, hence by definition we can conclude that these two protons are enantiotopic. I hope it is clear to you. If this replacement process seems hectic to you, you can do one thing, that you can figure out in this molecule there will be a plane of symmetry which will be passing through the plane of the cyclopropene ring. Okay, and with respect to this plane of symmetry, HA and HB will be mirror images of each other. Hence, by definition, if a molecule is having a plane of symmetry passing through it and the protons given are lying in exactly opposite faces, then these protons will be called enantiotopic protons. Okay, a similar three similar type of molecules are again given here, and you will have to figure out that these protons which are indicated with pink color are chemically equivalent or not. Okay, and let us figure out one by one. So in this first example, if you look at this particular proton is having a hydroxyl substituent adjacent towards the adjacent carbon, and these two are lying in the same phase. Whereas the other proton, which is lying in the opposite phase, and it is away from this hydroxyl group. Hence, these two protons cannot be called as being in an chemically equivalent environment. Okay, these are not present in the same chemical environment. Hence, you can conclude that the first molecule is having these two protons diastereotopic. Okay, and you can also figure it out by using the replacement process. If we replace this proton by deuterium, you can figure out the absolute configuration of this carbon atom, which is going to be diastereomer to the structure which you will get by replacing this proton by deuterium. Okay, for instance, let us solve the absolute configuration of these two centers. Okay, let us assume this proton has been replaced by D. So, in this particular structure, the absolute configuration of the first carbon will be, this will be assigned to be 1, this will be 2, this methyl substituent will be 3, and the proton which is not shown here will be of 4th priority. Hence, the first center is having an R configuration. Okay, now we will figure out the absolute configuration for the second carbon. So in this case, now we have first priority group in this way, second priority group in this way, and out of the protons we have replaced one by deuterium. So this will be third priority, and below the plane one will be fourth priority. So from moving by 1 to 2 to 3, this will be having an S configuration. So overall, the molecule after replacing this proton by deuterium is having a pair of R and S absolute configuration. Okay. Now we are going to replace the other proton by deuterium. So in that case, you will get first priority group here, second will be here, third will be here, and fourth group will be above the plane. Hence, since fourth group is above the plane, the absolute configuration will be reversed, and the overall configuration for the molecule this time will be R. So now if we compare these two pairs of absolute configuration pairs, RS and RR are diastereomers. Okay, and if you are asked that what will be the enantiomeric pair of RS, it will be SR. You'll have to reverse all the absolute configuration of the pairs. Okay, so these two are having enantiomeric relationship, but in this case, by replacing the protons with deuterium, we are getting a set which will be diastereomeric to the RS pair. This is why these two protons will be called diastereomeric protons or diastereotopic. Okay, I hope this is clear to you. Now we will move to the next pair of protons. Okay, in this case we are given these two protons and we have to figure it out. These are whether homotopic or enantiotopic or diastereotopic. So if we replace these two protons again by deuterium, suppose we are replacing this proton by deuterium, so in that case above the plane we will be having the second priority atom. Okay, and chlorine will be getting the first priority. Here deuterium means it is the third priority and here it is the fourth priority. So the fourth priority group cannot be in on the plane if we are figuring out the absolute configuration. We have to take it either above the plane or below the plane. Okay, so we are going to interchange these pairs of substituents, and if we interchange that, the third priority group will come here, the second priority group will come here, and the fourth priority group will come in place of the first priority, and here it will be the 1. Okay, and now if we move from 1 to 2 to 3, we are going to get the R configuration. Okay, so we have figured out if we replace this deuterium, the configuration is going to be R. But again, if we replace this proton next by deuterium, the absolute configuration will be exactly reverse of what we got initially, which is R, and in the second replacement we are going to get absolute configuration S. And as we know, R and S are a pair of enantiomers. So by replacing the protons by deuterium, we are getting a pair of enantiomers. That is why we'll have to say that these two protons are enantiotopic and they are chemically equivalent. I hope this is clear to you. Okay. Similarly, in the next molecule, these three protons which are highlighted with pink are given, and we have to figure out these are homotopic, enantiotopic or diastereotopic. So if you look at These all three protons are in the same chemical environment. Okay, because this aliphatic center can rotate freely. So all these three protons are chemically equivalent. Hence, these three protons are homotopic. Now here we have two sets of molecules. So in this case, if we look at these two protons, one of these two protons will be in the same phase of this hydroxyl group. Okay, and the other, suppose this is above the plane and placed towards us, and this is below the plane. Okay, so these two protons will be on the same phase, whereas these two protons will be on the opposite phase. Hence, you can say that the protons which are colored with pink are not in the chemically same environment, and these two will be diastereotopic protons. And for the second molecule, if you look at, if we use the replacement method, if we replace this particular proton with deuterium, the absolute configuration of this carbon center, let us figure that out. Okay, so in this case, the first priority group will be here, the second one will be here, the third group will be here, and the fourth group is going to be here. Hence, the absolute configuration will be R. And next, if we replace this proton by deuterium, it will be somewhat like this. Since fourth group is above the plane, the configuration will be reversed and it will be S configuration. Hence, These two protons will be enantiotopic protons. Same thing you can figure out for these two protons, and you will notice then that these two are also enantiotopic protons. Hence, these four protons will be enantiotopic and chemically equivalent. Again, here we have given three more molecules where you have to figure out that these protons which are colored in red are homotopic, enantiotopic or diastereotopic. So for the first molecule, you can clearly see that both these two protons are present in same chemical environment. Hence, you can tell that these two protons are homotopic and chemically equivalent. For the second molecule, if you see, this proton is in the same phase of this phenyl, and the second proton is in the same phase of this hydrogen. Hence, the two protons which are colored in red are not present in same chemical environment. Okay, hence these two will be called diastereotopic protons, and these are not chemically equivalent. And again, in this molecule, you can simply use the replacement method, or you can use the plane of symmetry method. Okay, if you imagine a plane which passes through these two substituents, that means these two substituents are contained by the methyl and hydroxyl group, then these two protons will be mirror images of each other. Hence, these two protons will be enantiotopic protons. You can also try to figure out the RS configurations by replacing each of these protons by deuterium. In the next question, it is said that identify the indicated pairs of hydrogens in the following compound as homotopic, enantiotopic, or diastereotopic hydrogens. Write the answers as 1, 2, or 3. Also write the number of unique or discrete hydrogens for each compound. So at first, HA and HB relationship is asked. You have to say these are either homotopic, enantiotopic, or diastereotopic. So if we look at HA and HB, we will see that HA are in the same phase of a hydroxyl group, whereas HB is in the opposite phase of the next hydroxyl group. Hence, these two protons are not present in the same chemical environment, and that is why, by definition, HA and HB will be diastereotopic protons. Okay. Next, we have been asked about HA and HC. So, you can take it as homework. You can figure out what relationships are HAHC, HBHT, and HAHT are having. Okay. Let us now solve this question on prochirality. Okay. So two molecules are given here, and you are asked the correct topicity of HA and HC in the following molecules is whether HA and HC are pro R or pro S. You have to figure out. Let us now solve the prochirality of the molecules one by one. Okay. Here we have taken the first molecule which is given, and first we are going to replace this HA proton by a deuterium atom. And after replacing the HA proton by deuterium, you can see that observing from here, the priorities look like this. Okay, and if we move from 1 to 2 to 3, it is moving in clockwise, hence it is R. Okay, hence the HA proton in the first molecule is a pro R atom. I hope this is clear to you. And in the next molecule, it is asked that you have to figure out the HC proton, whether it is pro-R or pro-S. So we will now replace this HC proton by deuterium in this way, and you will just have to figure out the absolute configuration now. For that, we will place our I here, and it will be of priority wise 1, 2, 3, 4, moving in the clockwise direction, and the absolute configuration will be R upon replacing HC by deuterium. Hence, we will have to conclude that the HC proton in the second molecule is a pro-R. Thus, if we go back to the question, option 1 will be the correct answer, because for both the molecules we have gotten that the molecules are pro-R. The atoms which are mentioned are pro-R. In the next question, we have been given a set of different organic molecules where the protons which are indicated with dotted boxes are have been asked to identify as homotopic, enantiotopic, diastereotopic or heterotopic. Okay, till now we have already solved a few such questions. So now I hope it is already easier for you. Let us try to solve these one by one. Okay. In the first molecule, you have been asked that whether these two methyl groups are homotopic, enantiotopic, diastereotopic or heterotopic. So suppose we are replacing this CH3 by CD3, okay? If we replace one of these by CD3, the structure will somewhat look like 1, 2, 3, and the fourth priority will be the proton, which is not shown, and the absolute configuration will be R. And secondly, if we replace this methyl group by CD3, we are going to get 1, 2, 3. And fourth group will remain in the same position, and the absolute configuration is going to be S. Hence, we are getting a pair of enantiomers this time by replacing the methyl groups by CD3, and that concludes that these two methyl groups are enantiotopic. Okay. Now we will go to the second molecule. So in the second molecule, there are two sets of protons which are shown. So we will solve the question for both these sets, okay? Just like we solved the first question, you can figure out that this set which is given is going to be enantiotopic. You can solve it by replacing each of these protons by deuterium, okay? And you will know that we will get a pair of enantiomers by replacing them. Hence, these two, you can figure out that these are enantiotopic. And if we look at these two protons, we will know that this particular center is not chiral, okay? Because these are connected to these two identical substituent groups. Okay, the ester groups are identical on both sides. Hence, these two protons are actually present in the same chemical environment. That makes us conclude that these two protons are homotopic. Now we are moving to the third molecule. So in the third molecule, we can see that it is a planar molecule, but this proton is present in the same phase of this bromo substituent, whereas this proton is present in the same phase of this ethyl substituent. Hence, these two protons which are shown with the dotted boxes are not present in the chemically same environment, which make these two protons as diastereomeric protons. Okay, let us move to the fourth molecule. So in this fourth molecule, we have been asked to assign topicity to these two protons. Okay, so first we will replace this hydrogen by deuterium, and the priorities of these groups will look like 1, 2, 4, 3, and the absolute configuration will be S. Similarly, if we replace this hydrogen by deuterium, the priority will look like 1, 2, 3, 4. And the absolute configuration will be S because the fourth group is okay. So in the first case, this will be R because the fourth group is present above the plane. Yeah. And in here, the fourth group is below the plane. So it will be S. Hence, we are getting a pair of enantiomers by replacing the protons present in the fourth molecule. So these two protons will be enantiotopic protons. So I hope the topicity of these four molecules are clear to you. Now we will move to the next molecules given, okay? So in the fifth molecule, if you notice, these two protons will be lying exactly in the identical chemical environment. Hence, these two will be homotopic protons. And in the next one, if you see, this proton is in the same phase of this ethyl substituent, whereas this proton is present in the same environment of same phase with this methyl. Okay, hence these two protons are not present in the same chemical environment, and this is why these two protons will be enantiotopic, distereotopic protons. Now, in this particular example, although there has not been shown any stereochemistry to the hydroxyl group, but it will be either above the plane or below the plane. Okay, this cannot be linear. So, one proton of the shaded box will be lying in the same face of the hydroxyl group, whereas the other one will lie on the opposite face of the hydroxyl group. Hence, these two cannot be called as to be in the same chemical environment. Hence, these two will be chemically non-equivalent. And these two will be distereotopic protons. In the next one, we have a planar ring here where on the alpha position we have these two protons which we have to assign the topicity. So you can imagine a plane of symmetry passing through the cyclopentanone molecule, and both the protons on the alpha position will lie above and below the plane. Hence, replacement of each of these protons by a deuterium will lead to a different enantiomer. Okay, you can also figure out the absolute configurations by replacing the protons by deuterium. And that will make this pair of protons enantiotopic. Let us then move to this next molecule. In this molecule, again, you can see that this proton is present in the same phase of this hydroxy group, whereas this one is present in the opposite phase of the hydroxy group. Hence, these two protons in the shaded box will be diastereotopic. Again, in the next molecule, this methyl and this proton are on the same phase, and this proton is in the opposite phase of the methyl. Hence, these two protons will also be diastereotopic. In the next one also, this proton and this methyl are on the same phase, whereas this proton is on the opposite phase. Hence, this set of protons will be also diastereotopic. In this example also, it will be same. The protons will be diastereotopic. And in the last one, if you see, there will be a plane of symmetry which will be passing, containing the cyclobutane ring, and both these protons are also present in the same chemical environment. Okay, and both these two substituents are identical, hence replacement will not lead to enantiomers, rather they will give identical structures of the molecule. Hence, the last pair of protons are going to be homotopic. I hope this was clear to you. You can take a screenshot of the answers for all these molecules given. Let us now move to the next question, where you have to indicate the relationship between each of the compound pairs below, and you have to state whether they are enantiomers, diastereomers, constitutional isomers, or identical compounds. So let us solve these questions one by one. For the first pair, what you can do is you can try to figure out the absolute configurations of the chiral centers present. Okay, suppose for the first example, if we look at, this will be first priority, this will be second priority, the below the plane will be the third priority, and the hydrogen will be the fourth priority. So the fourth priority group is present on the plane of paper. Hence, we will have to exchange these two, and the third will come here, fourth group will go below the plane, first will come here, and the second will come above the plane, and the absolute configuration will be hence S for this center. Now we will do the same for the next chiral center in the molecule. This will be the first priority. Sorry, the fluorine will be the first priority. This will be the second priority. The hydrogen will be the fourth priority, and the methyl is going to be the third priority. So again we will have to exchange because the fourth group is on the plane. Thus, here it will be 4, here will be 3, here it will be 2, and here it will be 1. Hence, if we move from 1 to 2 to 3, it will be again S. Hence, both the centers present in the first molecule are having S absolute configuration. Okay, now we are going to do the same for the second molecule. Here it will be 1, here it will be 2, here it will be 3, and here above the plane it will be 4. And the absolute configuration is going to be R because the fourth group is above the plane. And similarly, it will be second here, fourth here, third here, and first here, first here, and third here. So the configuration is S because the fourth group is present above the plane. Hence, the set of chiral centers present here will be R and S. And as we know that SS and RS will have a relationship of diastereomers. Okay, hence the first pair of molecules which are given are a pair of diastereomers. I hope it is clear to you. Let us move to the next questions. Now we will do the same for this pair, okay? And for this pair, you can do the same as we have solved the first pair. It is exact similar question, and you just have to figure out the absolute configurations of the chiral centers present, and you will know whether these are identical enantiomers, diastereomers, or constitutional isomers. Now, in this pair, in the second pair, we can see that both the substituents are exactly opposite in the second molecule, okay? If we draw the cyclohexanes, we will see that here it will be methyl above the plane and hydroxy below the plane, whereas the substituent positions will remain same, but the faces will be exactly opposite. Hence, this makes these two pair of organic molecules enantiomers of each other. You can also try to figure out the absolute configurations of the chiral centers, which will also be telling you that these two organic molecules are enantiomers of each other. Okay, so this you can solve as a homework, and we will solve this pair now. So imagine an axis of symmetry passing through these two carbon atoms, and if we rotate this molecule by 180 degree, this is the axis of symmetry, and if we rotate it like this by 180 degrees, you will see that these three substituents will move towards here. You can imagine the axis of symmetry passing through the midpoint, okay? And If you rotate it by 180 degree, you will get exactly this particular structure of the molecule. Okay. Hence, a simple rotation by an axis of symmetry is giving us the second molecule of the pair. That makes these two molecules identical. Okay, so these two molecules given will be identical. Now we will move to the next pair of molecules. So in the next pair we have these two. Okay, here the double bond, if you look at, will be a cis double bond, whereas this double bond is trans. And the cis trans pair will always be diastereomers of each other. Hence, you can conclude that this pair is a diastereomeric pair. Now, we will solve the same thing for these two Fisher projections given. Okay, for that we can simply figure out the absolute configurations. First, let us solve the absolute configuration of these two centers. So for this one, here it will be 1, 2, 3, and the configuration will be S. For the second carbon atom, it will be 1, 2 again, and 3. And the configuration will be R. Let us do the same for the second molecule, which will be 1 here, 2 here, and 3 here. And the configuration will be S. And for this one, it will be 1, 2, and 3. And the configuration will be S. Hence, the sets of the configurations are SR and SS. And as we know that SR and SS pairs will be diastereomers of each other. Let us go to the next pair now. So again, for these two pair, if you see that these two molecules are not mirror images of each other, hence they are neither identical nor enantiomers. These are rather diastereomers. Okay, and for this pair you can solve in the same way we solved this particular pair of example, and you will see that these two pair are actually enantiomers of each other. Okay, and now we are going to solve this pair. Here it will be 1, 2, 3, S, and this one will be 1, 2, 3, R, and these two pairs will be enantiomers of each other. Similarly, for these two pairs also, you can figure out the absolute configurations of the pairs. For instance, this will be 1, 2, 1. This one will be 2 and this one will be 3. Hence, this is going to be R. The first atom will be R. And the second one will be 1, 2, 3, S. Here it will be 1, 2, 3, S. Sorry, R, S, S. And here it will be 1, 2, 3. Okay, I must have made some mistake in this one. This first pair, the first pair I have made a mistake. This will be S. Because the fourth priority group is below the plane. And here it will be 1, 2, 3, S, and 1, 2, 3 will be R. So the pair of absolute configurations for these two molecules will be SS and SR. And these two pairs are diastereomers of each other. Hence, this particular pair will be diastereomers. I hope this is clear to you. You can quickly take a screenshot of the answers for all the molecules which we have just now discussed. Okay, so till now we have solved enough of the enantiomers and diastereomers related questions. So lastly, here you have to label these organic compounds given as whether they are chiral or achiral. For that, you just have to figure out whether these molecules are possessing chiral centers in them or not. So in the first molecule, if you see, there is a chiral center present, but this molecule is actually symmetrical. Okay, this is having a plane of symmetry in this direction. Okay, hence overall this molecule will be achiral. In the next molecule, if you see, this is a chiral center present and this molecule is not symmetrical, hence this molecule is chiral. Again, the third molecule, if you see, although it is having chiral centers, it is actually meso compound and it can be divided into two equal halves with respect to a plane of symmetry passing through the molecule. Hence, this molecule will not be chiral and it is a meso compound. In the next compound, there are no chiral centers present and it is a symmetric molecule. Hence, it is also achiral. In the next compound, you see that this is a chiral center present. Hence, this molecule is chiral molecule. In the next molecule, although we have two chiral centers present here, this molecule can be divided into two equal halves with respect to this plane of symmetry. Hence, overall, this molecule will not be chiral. It is a meso compound. Again, for this molecule, if we rotate the molecule by 60 degree, this molecule will be exactly symmetrical. Hence, although there are two chiral centers present, this molecule will also be a meso compound and hence it is not chiral. And lastly, in this last molecule, if you see, there will be a chiral center present which will be the below carbon of this Newman projection and hence this molecule will be chiral. Okay, I hope you could figure out the chirality of these molecules easily. Hence, we have come to the end of the tutorial questions. So today we had solved a few questions on the topicity of organic compounds, topicity of protons in organic molecules, as well as RS absolute configuration. We also solved a few questions on enantiomers, diastereomers, and identical compounds. And we saw how to approach such questions where you have to figure out the relationships. Okay, so thank you very much for joining. We will be continuing the tutorials again on next Friday, where we will be solving questions for the week 6 topics. Okay, thank you.